Okay, so when most of us think about artificial intelligence, it's incredibly easy to just picture this, magic, invisible brain floating around somewhere in the cloud. But the reality is actually far more grounded than that. AI isn't just magic software, it's a very real, physical, layered stack of technologies stacked perfectly on top of one another. And honestly, understanding how this physical architecture actually works is absolutely the best way to make sense of this massive, highly consequential tech rivalry that's unfolding right now between the United States and China.
Here is the roadmap for today's explainer. 1. The three-layer AI stack. 2. Hardware and the silicon bottleneck. 3. Models and engineering extreme efficiency. 4. Apps and the multimodal data engine. And finally, 5. The next AI battlefield.
All right, let's dive right in with Section 1, the three-layer AI stack, breaking down the magic.
The absolute most crucial point to grasp right away is that AI is not just one single thing. We really need to ground this abstract concept of AI in physical reality. Basically, the AI stack is a structural architecture made up of 3 distinct layers. You've got the hardware at the very base, the model sitting in the middle, and the application right at the top. And here's the kicker. Each layer is completely 100% dependent on the layer right below it to function. If you pull out the foundation, the entire thing just collapses.
That takes us to Section 2, Hardware, the silicon bottleneck, building the engine. So, looking at the absolute bottom of our stack, the hardware layer, it literally all starts with silicon. Now, silicon is a semiconductor. That means it naturally blocks electricity, but if you hit it with just a tiny electrical charge, it suddenly lets power flow right through. This unique property allows human engineers to carve these microscopic switches into the silicon itself. These switches act like tiny little gates, rapidly flipping electricity on and off, the zeros and ones of computer code. And when you cram literally tens of billions of these microscopic switches onto a piece of silicon about the size of your fingernail, you get a monstrous engine capable of processing immense, parallel mathematical calculations.
And that brings us to what is, without a doubt, the most important chip in the AI world right now. The GPU, or Graphics Processing Unit. What's wild is that originally, these chips were designed entirely for video games. They were just meant to render complex graphics and cool shadows for gamers. But in this massive twist of fate, researchers realized that this exact same grid-like architecture is literally the absolute best engine for doing the immense mathematical operations that AI requires.
But here is exactly where the physical tech collides head-on with geopolitics. You see, producing these top-tier GPUs requires what is arguably the most complex physical manufacturing process in human history. It heavily relies on American technology and patents, Taiwanese manufacturing at TSMC, and super-specialized European and Japanese machinery. And recently, a series of U.S. export bans effectively choked off China's access to this critical hardware layer. They were blocked from using TSMC's manufacturing, completely banned from buying NVIDIA's most advanced GPUs, and cut off from the highly specialized laser machines and chemicals needed to build their own chips domestically. So overnight, it created this massive, immediate bottleneck.
Which leaves us with this truly fascinating engineering puzzle. I mean, think about it. If you are suddenly cut off from the very best chips on the planet, how do you possibly build world-class AI using older, stockpiled, and frankly, weaker hardware? Let's find out in Section 3, Models, Engineering Extreme Efficiency. The software pivot. Okay, to understand this middle layer, the model, we first have to talk about the blueprint it's built on. Back in 2017, American researchers introduced something called the transformer architecture. Before this, AI read text basically like we do, just one word at a time. It would often forget the beginning of a really long sentence by the time it finally reached the end. But the transformer revolutionized the whole field by looking at an entire massive block of text all at once. It draws these invisible mathematical connections between concepts so it never loses context. And this right here is the foundation for pretty much every large language model we use today. The catch, though, is that running a massive transformer model usually requires thousands of those state-of-the-art GPUs. So Chinese engineers at companies like DeepSeek had to completely rethink what efficiency looked like. Just look at the difference here. In a traditional dense model, asking a single question causes the entire massive brain to light up, which honestly wastes immense computing power. To fix this, DeepSeek took a technique called mixture of experts, or MO, and pushed it to an absolute extreme. They literally sliced the AI's brain into 256 tiny, hyper-specialized experts.
Now, when you ask it a question, an ultra-efficient router instantly kicks in and activates just 8 of those tiny experts, leaving the rest of the brain completely asleep. It is incredibly efficient.
But wait, they didn't stop there. They paired that fragmented brain with a totally new technique called multi-head latent attention, or MLA. The easiest way to think about this is like extreme memory compression. When you're having a conversation with an AI, it has to hold the context of the chat in its short-term memory, which usually eats up a huge amount of GPU power. Well, MLA actually shrinks the AI's short-term memory footprint by over 90%. The system perfectly keeps track of its thoughts, but it uses drastically less memory, making it unbelievably cheap to run.
And amazingly, they optimized even deeper than the architecture itself. They completely changed how the software talks to the hardware. Normally, NVIDIA provides this industry-standard software called CUDA. It's essentially the automatic transmission of AI development. It's super fast, reliable, and just does the work for you. But DeepSeek couldn't just rely on that standard software because they were using older chips. So they built an intermediate assembly layer called PTX. Basically, they shifted from automatic into manual transmission. They wrote highly customized, low-level code just to force their older, stockpiled chips to communicate and process calculations with maximum possible efficiency.
So, what is the final result of all this extreme, necessity-driven engineering? DeepSeek managed to build and train a world-class foundational AI model for reportedly just under $6 million. Let that sink in. That is a completely jaw-dropping number when you realize that Western competitors, who can basically just buy more hardware instead of meticulously optimizing their code, have been spending hundreds of millions of dollars to train their models.
Moving right along to Section 4, Apps, the multimodal data engine, fueling the brain.
So you have this incredibly efficient brain, right? But to teach an AI about the real physical world, plain text just isn't enough anymore. You need multimodal data, high-definition video, audio, images. The American approach has mostly been just scraping the open internet, but they're starting to hit a wall. They are literally running out of high-quality text, the videos they scrape are often heavily compressed, and they're facing all sorts of strict copyright and privacy hurdles. China, on the other hand, holds a very unique structural advantage here. Their digital economy is entirely dominated by consumer super apps. This gives them an infinite, growing pipeline of perfectly labeled, native, uncompressed video files, complete with exact user engagement metrics, just sitting right there on their own servers. And this dynamic is exactly why Chinese AI models, like Cdense 2.0, are suddenly producing these hyper-realistic viral videos. Take ByteDance, for example, the parent company of apps like Douyin and TikTok. They don't have to just scrape the internet. They literally own the platform. When their AI trains, it has direct access to the exact metadata. It sees the lighting, the camera angles, the specific human engagement. This flawless, native data drives what engineers call natural motion synthesis. Physics, reflections, sound, it all syncs up perfectly, and it completely surpasses competitors who have to rely on heavily compressed, fragmented data scraped from the web.
Which brings us to our final part, Section 5, the next AI battlefield, moving beyond the screen.
When you look at this timeline, it is moving at lightning speed. In 2016, we saw a machine finally beat a human champion at Go. That was a massive wake-up call that sent global AI investment into overdrive. By 2017, the transformer architecture was introduced, completely redefining that middle model layer. And less than a decade later, looking toward 2026, highly efficient world-class models like DeepSeek and Cdense are launching. They are literally bypassing hardware bottlenecks through extreme software optimization and these massive multimodal data engines. We are witnessing a technological race happening simultaneously across all 3 layers of the AI stack. But here's the thing, the models of tomorrow aren't just going to live on our computer screens. They are going to power physical robots and autonomous agents operating right here in our physical reality. Which leaves us with this final, really critical thought to chew on. As we hit the limits of scraping the digital internet, if the future of AI requires truly understanding the physical world and real human behavior, where will that next massive trove of data actually come from? Will it require entirely new hardware, a completely new model architecture, or an application layer we honestly haven't even dreamed of yet? Thank you so much for joining me for this explainer, and as always, keep learning.